In this video cycle, I would like to explain some well-known vulnerabilities in attacks used to gain remote access. And the first one is buffer overflow. I'm going to explain the theory of this vulnerability, and in the next video we will do some practice with Metasploit exploits. Okay, so what is the buffer? Buffer is the memory space which is used to keep temporary data created by programs or entered by user. Programs and system allocate certain space of the buffer to hold this data. If the program is wrongly designed or configured, it can occupy more memory space than it was dedicated. And it can cause program crash. Attackers use this vulnerability to execute malicious code. Let's take a look how it happens. We have a buffer and program allocated 3 bytes to store some variable. The user entered some big value which has 5 bytes. Because the program is wrongly designed, it doesn't check user input and buffer boundaries. And this is what happens. The rest of the bytes occupy memory space, which is probably dedicated for other variables. In normal situations, the size of the data must be checked before placing into the buffer. There are several types of buffer overflow, and in this video we will consider stack-based buffer overflow. First of all, let's consider what the stack is and what properties it has. Stack is created to keep arguments and variables of functions. As you know, programs contain a lot of user-defined functions which are designed for certain tasks. Stack has LIFO structure which stands for last input, first output. Please look at animation to understand how it works. Also, please remember that stack always grows from higher address to lower ones. Now, I would like to explain what registers of processor are used with stack. The first one is ESP, Extended Stack Pointer. It always contains address of the top element in the stack. So when the new element is added to the stack, the value of stack pointer is decremented. Extended base pointer is used for quick access to the variables and arguments stored in the stack. And finally, extended instruction pointer has address of the next program instruction to be executed. As you know, compiled program consists of set of simple instructions for processor, which is also called machine code. This set of instructions is loaded into the memory, and processor executes them step by step on the basis of value in extended instruction pointer. Okay, we have basic information about stack and registers. Now, let's consider how stack operates. Let's imagine that we have the following program code. It consists of 2 functions, main and getInput. GetInput is called from main. In the getInput we define variable name and reserve 10 bytes in the memory to keep the value of given variable. Then, with the function gets, we ask user to enter any value with which is then assigned to the variable name. Program code, or just set of instructions, is stored in the separate memory space. When function getInput is called, the stack is created, and stack pointer contains address of the last element in the stack. As the first element, we place argument of getInput function. In our case, we don't have argument, but anyway, the place is reserved in the stack. The base pointer is set to 0, and instruction pointer contains address of the next instructions to be executed. Then ESP is decremented and points the second element in the stack. At the same time, the value of EIP register is placed into the stack as the second element. This register contains address to come back to the main function when getInput completes its task and stack is destroyed. As you can see, the next comment in the main function is exit, so we must return control to given function after getInput function. And again, ESP is decremented and the value of EBP is placed into the stack as the third element. After that, the current value of ESP is copied to EBP register. Now we are inside getInput function. For the variable name, we need to allocate 10 bytes. That is why the value of ESP register is decremented by 10 bytes instead of 4. Okay, we just created a stack frame which contains return pointer, argument, and variable of getInput function. The next step we need to do is to initialize our argument and variable. So how to access certain element in the stack? In this task, extended base pointer can help us. If you remember, EBP contains address where the old value of EBP is stored. This address will be used as the pivot point to access all the elements in its stack frame. For example, if we want to access the first element, we just increment EBP by 8 bytes. But if we want to access name variable, we just decrement EBP by 10 bytes. In our case, user entered hello string and this value was placed into the stack. Now we need to release the stack and return control back to the main function. Because stack has leaf structure, we start with the last element and then move to the next one by incrementing ESP register. The value of the last element is deleted or assigned to another register depending on the program. In our case, it's just deleted. Again, we increment ESP value to move to the next element in the stack. Old value of base pointer is copied to EBP register and removed from the stack. On the final step, the return address is copied to EIP register and control is returned back to the main function. The first stack element is also removed and stack is completely released. I hope my explanations were clear and you understood the basics of stack operations under normal conditions. Now let's consider what happens when stack is overflowed. We have the same vulnerable program with created stack. Now let's see what happens when user enters some value. User entered hello string, which takes 5 bytes, and this is how it looks in the stack. So if user enters any value less than 10 bytes, the program will work well, as it should. But what happens if user enters something bigger? This time user entered the following value, and it takes 20 bytes. How does the program put this value into the stack? Well, it's simply overwrite all values in the stack. The bad news is that we overwrote return address. The program will try to execute instruction on the base of this address. The behavior of program becomes unpredictable, but in most cases it will simply crash. But if we put malicious executable code into the stack, we can execute it by modifying return address. This code can create a remote shell to attacker's machine, and it's known as a shellcode or bytecode. In this video, I would like to show you how to gain access using buffer overflow vulnerability. I intentionally chose simple program and exploit to better understand this type of vulnerability. As the vulnerable program, I'm going to use the free software Icecast, which is used for audio and video streaming, and works as a server. Let's open a security bulletin to get some information about vulnerability in Icecast. On the top of web page, there is a short description of security flaw. If we scroll down, we can read more details. The idea is to send crafted HTTP requests to Icecast server. The graph.http request will cause buffer overflow and provide remote access to computer. Now let's open Exploit database. In the search bar, type icecast keyword and press Enter. Click on this entry. From here, you can download vulnerable software and test it. Also, there is a raw code of exploit which we are going to review. Don't worry if you are not familiar with the Ruby language or you don't have programming skills. I will explain the basic idea of how exploit works. The code consists of two functions. The first one is initialize. It's a standard function of all Metasploit exploits, and there is nothing interesting here. The second function is exploit. The function just constructs special HTTP request in the following rows. In the end of request, the special sequence is added to overwrite return address. And finally, the graph.http request is simply sent to the server. Now let's try to run exploit. On Windows machine, launch icecast and enable server mode. On Kali, execute the following commands. As the payload, I'm going to use Meterpreter, which creates a remote shell. Meterpreter has a lot of useful features, and we will consider them in details in post-exploitation unit. And we have Meterpreter session. From now, we can manage remote Windows machine. Our attack was successful.